All right, let's jump right in. Today, we're pulling back the curtain on a technology that's quietly powering a huge part of our digital world but often flies under the radar. Field Programmable Gate Arrays, or FPGAs. If that sounds complex, don't worry. Think of this deep dive as your ultimate shortcut to truly understanding these incredible devices, what they are, why they're so crucial, and maybe even how you might start playing around with them yourself. Our goal here is to cut through the jargon and give you a crystal clear picture from all the research we've gathered, making you well-informed and perhaps a little surprised by what they can do.
And what's particularly compelling about FPGAs, I think, is their unique position in modern electronics. They're not your standard off-the-shelf chip that does just one thing, nor are they really a general-purpose processor like a CPU. They represent this incredibly dynamic platform that can literally become almost any digital circuit you need. It's this adaptability combined with their raw processing power that makes them indispensable in everything from, cutting-edge data centers to satellites orbiting Earth.
So let's start with the big differentiator then. What exactly is an FPGA? The key is right there in the name. Field Programmable. Unlike application-specific integrated circuits, or ASICs, which are custom designed and, well, fixed once manufactured, kind of like a specialized tool built for just one job. FPGAs are designed to be reprogrammed after they're made. You basically buy a generic FPGA chip, and then you decide what hardware it'll become.
Exactly. And that ability to reprogram a chip after it's left the factory, sometimes even after it's been deployed in a remote system, is a fundamental game changer. I mean, imagine a piece of hardware, say, in a satellite, or maybe an industrial robot in a distant factory. If you discover a bug, or perhaps you want to add a completely new feature, you don't necessarily need to physically swap out the chip. You can push an update that literally reconfigures the hardware on the fly.
Wow.
And this flexibility directly translates to a much longer hardware lifespan. It can dramatically reduce maintenance costs, and it allows companies to get products to market much faster, knowing they can adapt later.
That's a huge advantage right there. A really huge advantage. Now, if we look inside an FPGA, our sources show us they're primarily made up of two main things. An extensive grid of what are called configurable logic blocks, or CLBs, and then this incredibly sophisticated network of programmable wiring, connecting everything up.
Right. The CLBs are sort of the workhorses, the computational core. And at the heart of each of those CLBs are tiny programmable blocks called lookup tables, or LUTs.
LUTs, okay.
Think of an LUT as a miniature, instantly reconfigurable calculator almost. You can load different configuration data into it, and it will immediately perform any basic logic operation you need, from a simple AND gate to something more complex. This instant adaptability, along with things like flip-flops for storing data state, is how an FPGA can transform from a generic chip into almost any digital circuit you can imagine, just by changing its configuration data.
That instant adaptability is pretty wild. So if the CLBs handle the core logic, how does all that internal calculation then talk to the outside world, other chips or sensors?
That's where the input-output blocks, or IOBs, come in. They're strategically placed around the edge, the perimeter, of the FPGA chip. They act as the programmable gateway between all that internal logic and the external pins of the device. They manage the flow of signals, input, output, sometimes bidirectional, and they can support a whole array of different electrical signal standards, which makes them incredibly versatile for connecting to almost anything. They are the device's essential communication channels.
Got it. So CLBs for logic, IOBs for talking to the outside, and then connecting all of these individual pieces is this intricate wiring network you mentioned, the programmable interconnects or routing resources.
Precisely. You can imagine it as the nervous system of the FPGA. These are vast networks of tiny metal segments and configurable switches, often called programmable interconnect points, or PIPs, or sometimes switch matrices. They're how all the individual logic blocks and IOBs actually communicate and form a complete functioning circuit. And it's worth noting here that the complexity of this internal wiring network, the routing, profoundly impacts both the final performance of your design, how fast it can run, and also the sheer computational time it takes for the specialized software tools, the EDA tools, to figure out how to connect everything. For very complex, dense designs, generating this wiring map, this routing solution, can sometimes take well over 10 hours.
10 hours. Just for the wiring.
Yeah, it's a significant practical bottleneck in the development flow. It really highlights the complexity inside these chips.
That really puts the sheer complexity into perspective.
Yeah.
And beyond those tiny bits of memory within the CLBs, like the LUTs acting as small ROMs, modern FPGAs also come with dedicated larger memory blocks, right? Often called block RAMs or BRAMs.
That's right. RAMs provide much more efficient, high-bandwidth data storage than trying to build memory out of the general logic fabric. They're crucial for applications that need to store or buffer significant amounts of data right on the chip. Our sources, I think, have a great summary table of all these components, the CLBs, LUTs, IOBs, interconnects, BRAMs. It really helps you visualize how these pieces fit together to create what is essentially programmable hardware.
Okay, so if FPGAs are these incredibly flexible, programmable chips, how do engineers actually, bring their designs to life on them? What's the process? It all starts with something called design entry, which usually means describing the desired hardware behavior using specialized languages called hardware description languages, or HDLs. Think of HDLs like VHDL, Verilog, and the more modern system Verilog as blueprints for circuits. They allow engineers to model complex electronic systems in text. And a big plus, apparently, is that the same HDL description can often be adapted to different FPGA technologies, or even used as a starting point for a custom ASIC, giving you amazing design portability.
That portability is key. Now, each of these HBLs has its own sort of flavor and history. Verilog, for instance, has a syntax that looks a bit like the C programming language. This often makes it feel quite accessible for beginners, especially those coming from software. And it's widely adopted, great for faster initial prototyping. It does have some limitations, though, like weaker type checking compared to VHDL.
And VHDL.
VHDL, on the other hand, is known for its strong typing and its, well, let's say, verbose and very structured syntax. This makes it really ideal for highly complex and safety-critical systems. Think aerospace, defense applications. It definitely has a steeper learning curve than Verilog, but that strong typing offers incredibly robust error detection early in the design process.
Okay, and then there's system Verilog. You mentioned that earlier.
Yeah.
What makes this language so important right now?
System Verilog. It's essentially a powerful extension, a superset of Verilog, standardized as IEE 1800. It incorporates features you might recognize from object-oriented programming languages like C++ or Java. But what makes it a real game changer isn't just the advanced design features. It's its ability to bridge that historical gap between hardware design and hardware verification. It effectively unifies HDL and what we call hardware verification language, or HVL, capabilities.
So design and test speak the same language.
Exactly. It means design teams and verification teams can work within the same powerful language framework. This streamlines a process verification that, honestly, can often consume 2 to 5 times more effort and time than the actual design coding itself in modern complex chips. So System Verilog directly tackles one of the biggest bottlenecks in complex chip development today, helping ensure high-quality, bug-free chips get to market faster. It provides advanced features like object-oriented programming for building reusable test environments, constrained randomization for generating smart test cases, and assertions for checking behavior automatically.
That makes perfect sense why it's so critical. 2 to 5 times the effort on verification. Wow. Okay, so after you've described your hardware with an HDL, the next absolutely essential phase is simulation and verification. You stress this as non-negotiable for ensuring your chip will be reliable, functional, and perform exactly as intended, especially given those, frankly, alarming low first silicon success rates. What was it, only 14%?
That's right. Verification is paramount. To do this, engineers build what's called a test bench. This is essentially a simulated environment built around the design under test, or DUT, your actual FPGA design. In this test bench, you can feed the DUT various inputs, control signals, and meticulously monitor its behavior, its outputs, to see if it matches the specification.
And you mentioned System Verilog helps a lot here.
Immensely. For today's incredibly complex designs, like a whole system on chip, it's physically impossible to manually write tests for every single possible input scenario or state. It would take lifetimes. That's where sophisticated automated verification techniques, largely enabled by System Verilog, come in. Things like constrained random verification, or CRV.
CRV.
Yeah, CRV lets you define rules or constraints, and then the tools automatically generate billions of random but valid test stimuli. For example, you could tell it to randomize network packet fields, but ensure the length is always, say, between 64 and 511 bytes, maybe with certain lengths being more common. It finds corner cases you'd never think of manually. Then you have System Verilog assertions, or SVA. Think of these as executable specifications, little monitors you embed in your code that constantly check if the design is behaving correctly according to specific timing rules during simulation. Like, if a request signal goes high, then an acknowledge must follow within 1 to 2 clock cycles. They catch bugs much earlier.
Like little watchdogs inside the simulation.
Precisely. And finally, functional coverage. This tells you how much of your specification you've actually tested. Instead of just running tests endlessly, System Verilog lets you define coverage points, interesting scenarios, or values you want to make sure your random tests have actually hit. You use cover group constructs for this. It helps you move from just running tests to achieving verification closure, having quantifiable confidence that you've thoroughly exercised the design's functionality.
Okay, that whole verification stage sounds incredibly deep and crucial. So once your high-level design is thoroughly verified in simulation, the next big step is synthesis, right?
Correct. Synthesis is where specialized software tools take your human-readable HDL code, your Verilog, or System Verilog, and convert it into what's called a gate-level netlist. Think of it like taking that detailed architectural drawing and breaking it down into a precise list of every individual logic gate, like LUTs, flip-flops, maybe some dedicated blocks like multipliers and how they need to be connected.
And you mentioned a key point for beginners here.
Yes, it's crucial for anyone starting out to understand the concept of synthesizable constructs. Not all HDL code you can write and simulate translates directly or efficiently into physical hardware gates. You have to write HDL code in a very specific structured way that implies hardware the synthesis tool understands. A common pitfall, for instance, is inadvertently inferring latches.
Latches.
Yeah, a latch is a type of simple memory element. If your code doesn't explicitly define what should happen in every possible condition, like in an if statement without an else, the synthesis tool might guess you want the output to hold its previous value, creating a latch. Latches can sometimes cause timing problems or unexpected behavior in FPGAs, so you generally want to avoid inferring them unintentionally. You need to learn to write synthesizable code.
Got it. Right for hardware, not just for simulation.
Mm.
Okay, so after synthesis gives you this list of gates and connections.
We move to place and route, often shortened to PNR. Now that you have that precise netlist, the PNR tools perform two critical tasks. First, place. They literally map each logic element from your netlist onto a specific physical location, a specific CLB, a specific IOB on the actual silicon die of the FPGA chip. Second, route. They figure out how to use the FPGA's vast network of programmable interconnects, those wires and switches we talked about, to physically connect all those place components according to your netlist.
So this is where the design really meets the physical chip.
Exactly. It's where the abstract logical design meets the real-world limitations and physical constraints of the FPGA architecture, things like how long the wires are, which affects signal delay and maximum operating speed. And as I mentioned, this PNR step is surprisingly complex computationally. It typically consumes the vast majority of the overall build time, potentially many hours for large designs.
Right, that's where the 10+ hours figure came from. Okay, so place and route is done. What's the final step to getting it onto the actual FPGA?
The final step is bitstream generation and programming. The PNR tools output detailed placement and routing information, which is then used to generate the bitstream. This bitstream is a proprietary binary file, essentially the final configuration blueprint that tells the FPGA exactly how to configure every single one of its internal connections, the contents of all its LUTs, the settings for its IOBs, everything. This is the file that transforms a generic, blank FPGA chip into your specific, custom-designed hardware.
And how does that bitstream actually get onto the chip?
It depends on the type of FPGA. Most common FPGAs are SRAM-based, meaning their configuration is volatile. It disappears when power is removed. For these, the bitstream is typically stored in an external non-volatile memory chip, like a flash memory, located nearby on the circuit board. When the system powers up, the FPGA automatically loads the bitstream from the flash. There are also flash-based FPGAs where the configuration memory is built right into the FPGA chip itself, making it non-volatile. These can be programmed directly and hold their configuration without external memory.
Okay, and you stressed earlier do the verification before this programming step.
Absolutely critical. Perform thorough, upfront verification in the simulator before you generate the bitstream and program the hardware. Why? Because debugging on a physical chip, trying to figure out what's going wrong inside the silicon, is far, far slower, more difficult, and more painful than finding those same bugs in a powerful simulation environment with full visibility. Trust me on that one.
Sound advice. Okay, so we've walked through what FPGAs are, how they work inside, and how designs come to life. Now let's talk about where you actually see these devices making an impact. Where are they used in the real world? Our sources show they're increasingly integral to high-performance computing in data centers. You'll find them in things like network-attached storage, NAS, storage area networks, and DMSAR, and high-performance servers. Especially, it seems, in FPGA-based network interface cards, or NICs, sometimes called smart NIs, where they're used to accelerate tasks like network processing, security functions, and even AI and machine learning workloads like neural networks or matrix multiplication, offloading the main server CPU.
That's a huge area. And in the aerospace and defense sectors, FPGAs are highly valued, as we touched on, for their resilience, their reliability, and their adaptability in mission-critical applications. Their inherent parallelism is great for signal processing in radar and communications, and specialized versions offer radiation tolerance, which makes them perfect for spaceborne systems like satellites and deep space probes, and also for secure military communications gear on the ground or in aircraft. And that unique value proposition we mentioned earlier, the ability to use radiation-hardened FPGAs in orbit that can literally receive new configuration files from Earth. That allows for in-orbit upgrades, bug fixes, or even completely new functionality years after launch. This isn't just a nice-to-have, it's often a fundamental requirement for extending mission life and adapting to new needs in environments where physical access is totally impossible or prohibitively expensive.
That in-orbit upgrade capability is just incredible. You also find FPGAs increasingly integrated into the automotive industry, don't you? Playing critical roles in areas like advanced driver assistance systems, ADAS, processing sensor data from cameras, radar, LiDAR, also in-vehicle infotainment systems, and the sophisticated networks, the gateways that connect all the different electronic control units within a modern car.
Absolutely. And closely related is telecommunications. FPGAs are vital players in the infrastructure for both wired and wireless communication networks. They handle demanding functions like high-speed packet processing, complex digital signal processing for radio signals, and managing the intricate, high-bandwidth connections needed for 5G and even the development of future 6G systems. What's particularly fascinating here is how their adaptability, their reprogrammability, allows these communication systems to genuinely future-proof themselves to some extent. As communication standards evolve, providers can often update the FPGA configuration rather than undertaking costly, time-consuming complete hardware redesigns. It provides a significant competitive edge in these very rapidly changing markets.
That future-proofing aspect is really powerful. And finally, a massive application area for FPGAs, maybe one of the most important financially, is in ASIC prototyping and hardware acceleration, right? Engineers use FPGAs extensively to build working prototypes of their complex system-on-chip designs, and crucially, to develop and test the embedded software that will eventually run on the final ASIC before they commit to that final, extremely expensive ASIC manufacturing process.
Yes, this is a critical risk mitigation strategy within the entire semiconductor design ecosystem. Remember that statistic. Only about 14% of complex chip projects achieve first silicon success, meaning the very first time they manufacture the actual custom silicon chip, it works perfectly without needing any fixes. FPGAs fundamentally transform that high-stakes, multi-million-dollar gamble of ASIC tape-out into a much more iterative, verifiable process. They allow engineering teams to literally build and test their complex hardware and software interactions on a real high-speed hardware platform before committing to the irreversible, massive, non-recurring engineering NRE costs and long manufacturing times of ASIC fabrication.
So it avoids those costly respins of the silicon.
Exactly. It's the ultimate try before you buy for developing complex hardware systems. It drastically reduces the risk of discovering major bugs late in the game, which can lead to crippling project delays and huge financial losses. For ASIC development, FPGAs are absolutely indispensable.
Okay, that makes a ton of sense. So what does this all mean for you, the listener, if you're curious about FPGAs and maybe thinking of dipping your toes in? Our sources definitely acknowledge that people new to FPGA development often encounter a pretty steep learning curve. It's not just about learning the syntax of an HDL like Verilog or VHDL or figuring out the complex software tools. It's really about a fundamental mindset shift, especially if you're used to traditional software programming. In software, you generally think sequentially, do this step, then this step, then this step. FPGA design, however, demands you conceptualize many operations happening simultaneously in parallel. It's true hardware design.
That parallel thinking is probably the biggest hurdle for newcomers.
Yeah, and common pitfalls for beginners often include things like mistakenly creating those unwanted latches we talked about, or maybe designing logic that relies on asynchronous signals, which can be tricky to get right, or improperly handling reset signals across the design. It's really like learning a whole new way to think about computation and timing.
It is. But it's definitely learnable. To navigate this, a structured learning path is highly recommended. First and foremost, get a solid understanding of digital logic fundamentals. This is absolutely indispensable. You need to be comfortable with concepts like Boolean algebra, combinational and sequential logic, state machines, and understand how basic elements like logic gates, LUTs, and flip-flops actually